Okay, hi everyone. We continue discussing lattices and Lie groups, and in fact, last time I defined lattices and Lie groups with respect to Haar measures, and now I want to tell you that actually it will be convenient for us to view the Lie groups as algebraic groups, or more precisely as real algebraic groups. So I'm introducing algebraic groups today. And this might be like a short introduction to the theory of arithmetic lattices. And I don't see why it's not. Okay, I think I will use that screen. Okay, so roughly speaking, algebraic groups are such groups that are defined by some set of polynomials such that the group operations are also polynomial morphisms. But let me introduce the notion of an algebraic variety. So by definition, the subset X in Cn is an algebraic variety, or it's an algebraic set if there exists a set of polynomials and now I will denote them by f alpha sitting in C x1 and so on xn, such that f alpha of x is equal to 0. So, okay, it's not good. So f alpha of x is equal to 0 for all elements in X and only for them. So I will, yeah, indeed. So this is, so f alpha of x is equal to 0 if and only if. Actually, I should write here such that for every alpha, right? If and only if x belongs to x. In fact, okay, so in fact, one can choose a finitely generated ideal of polynomials and so on. We will skip this discussion of algebraic varieties for now. We will only say that if polynomials are can be chosen to be with real coefficients, then it's going to be called a real algebraic variety. So if I would say if all f alpha can be chosen from k of x1 and so on xn, then x is said to be a k variety. Is a k variety or variety defined over k. Defined, which means it's defined over the field k. And an algebraic group, again, I'm actually omitting a lot of details, so we will probably discuss algebraic groups with more details a bit closer to the end of the semester when we start discussing arithmetic lattices, but for now it's enough. And we say that an algebraic group, so the second definition, G is an algebraic, okay, it's an algebraic K group if G is a K variety, is an algebraic K variety, and the group operations are polynomial morphisms. So, and the group operations are polynomial morphisms. What does it mean? It means that they can be described as polynomial maps, right, in the coordinates of G, right? So which means that, so the product, multiplication from G to G and the inversion from G to G. So here it's from G times G, it's the product, right? The pair is mapped to the product, and here any element is sent to the to G inverse. So these two maps can be written as polynomials. I would say, so it just are polynomially defined, right? And let me already start with examples. In fact, most of the classical simple, okay, in fact, actually any simple classical linear Lie group is actually even a rational algebraic group. So I will write it as a fact. Every simple linear Lie group is, okay, every simple, I should write every classical simple linear Lie group is an algebraic Q group. Let us start with probably the simplest one is actually not GLN, but SLN. SLN. So SLN is the set of matrices. In fact, I do not write here SLN of R or SLN of C by intents, since we will view, okay, we will try to view G as more like a scheme rather than a set, since there can be, we can consider an algebraic group with real points and complex points, and I will just say it a few minutes later. So generally, it is the set, so it's an element of the set of matrices n times n, which can be identified with, say, so again, I included everything in Cn, so this is Cn squared, right? And it's determined by the following equation, that A is equal to 1. So for A being a matrix Aij, right? That A is a polynomial in fact over Q. So remember that A, right, if you write it down, it is a, so for instance, it's the product of diagonal guys plus and so on, plus permutations of Aij's with under some certain rule. Well, basically I need to include all full cyclic products of elements in. Okay, so you see, as function, so that the determinant of A as a function with respect to coordinates A1, 1, and so on, A and N. So here, so this is an explanation, right? And my Cn squared is just a space with coordinates, right? Is a space with coordinates A11, A12, and so on, A and N, precisely N squared coordinates. Okay, so it is an algebraic variety, obviously, since it's defined just by one polynomial equation, right? This is a polynomial. This is a polynomial with coordinates, with respect to coordinates here of these coordinates, and just one equation we have. Okay, now why is it an algebraic group with respect to this definition? Okay, we have two group operations. I can say that it's clear that the product A times B, right? It's the matrix Cij, where Cij can be represented as the product of the row of A times the column of B. So it depends polynomially, right? Depends polynomially on variables Aij and okay, Bij, but I can write, in fact, different indices. But here I mean actually both, all possible pairs Ij, so I can write B, I don't know, St, right? But for all possible. So in fact, my Cij depends on this polynomially, which precisely means that it is a polynomial morphism. So the product, okay, the map from the product G times G to G, defined as just simply the product of matrices, right? And the product of matrices is a polynomial function with respect to matrix entries. So thus it is a morphism. It's clear that, so thus mu is a Q morphism. Here, I didn't actually write it here, but I want them to be K polynomial, right? Or polynomial K morphisms. which means that the polynomials are also, they also have coefficients from the field K, right? We specify the field. Okay, so in fact, this polynomial right here, it is just, again, a simple product of coordinates and combinations with coefficient being equal to 1. Okay, 1 or 0, since some of the variables do not participate in this product. So it is obviously a polynomial with coefficients from the field Q, not even R or C, even despite of the fact that this can be a complex Lie group, right? But as an algebraic group, it can be viewed as a Q or rational group. Okay, so in fact, I didn't say that the inversion also, so same holds for the map A to A inverse, since, again, remember, we just recall the linear algebra 1, how to compute the determinant of, how to compute the inverse of the matrix. You need to compute the determinant and the algebraic complements to any entry, which are, again, some determinants of some submatrices of A, right? The determinant here is equal to 1. We are sitting in SLN, so we just divide by 1. We don't have anything really bad. We just have polynomials, and that's a really great example. So this happens to be a Q group, and then we can notice the following. So one can consider for any algebraic group, so as a, again, as a general fact, that I skipped here, for any K group, one can consider, okay, for any K group G, one can consider the groups G of R and G of C of real and complex points.
Okay, so or so.
Yes, that's true. So I will specify. Okay, we always assume K being a subfield of C. Okay. So and yeah, okay, let it be indeed a real subfield. So yeah, that's true. So then one can consider the groups G of R and G of C of real and complex points. So generally, how can we define them? We remember that this is a subset of Cn, of some Cn, right? Then for this algebraic variety, it definitely just intersects Rn or Cn, or in fact, I can take the group of rational points as well. So one can consider the groups. I will even include G of Q. And we obtain them as follows. So we basically take G of any K as intersection of G with the space Kn, right? So we only include those solutions of the system of this system of polynomials, right? So in fact, algebraic varieties are just the set of zeros of some system of polynomial equations. So we can include all these roots, but here we collect only those that can be written, they can be taken from Kn, right? And this is my G of K. So, and the general fact is that G of R and G of C are respectively Lie real and complex Lie groups. And G of R and G of C are respectively real and complex Lie groups. So getting back to this example with SLN, I'm just writing, for example, SLN R and SLN C. So this is going to be a real Lie group, and this is going to be complex Lie group. Okay, so this example is very nice, since in fact already even in dimension when n is equal to 2, we have something that reminds us the isometry group of the hyperbolic plane. When n is equal to here, we get the isometry, well, okay, something close, something exogenous to the isometry group of the Euclidean, sorry, of the hyperbolic three-dimensional space. Okay, I can write also the following fact that algebraic, so not all Lie groups can be viewed as algebraic groups. So the setting, I would say that the category of Lie groups and algebraic groups are generally different. But if a Lie group G has finitely many components and it's linear, one can consider the adjoint representation, which gives some identification. So also algebraic groups allow quotients by the center. So as a continuation of this example, I will take that PSLN being the quotient of SLN by the center. I will here write just by plus minus identity. Is also a Q group, right? And this is interesting for us just because of the properties of hyperbolic geometry and isometries. So I just recall that isom plus H2 is PSL2 R, real points of PSL2, and isom plus H3 can be identified with PSL2C. The complex points of this group when n is equal to 2. Okay, so these are our examples. Okay, maybe I should also say something about GLN and SOPQ, and then we will, okay, I will switch the board. Example number 2. From G is GLN. Surprisingly, this is a little bit more complicated than SLN. Let us just describe how it is defined. So it is the set of all matrices such that the determinant is not equal to 0. It doesn't look like a polynomial equation, right? I mean, it's not an equation at all. So what you can do here? Well, this description is pretty good to say that GLN is a Lie group, right? Since it's basically just an open subset in Rn squared or Cn squared, depending on which field you consider. But to get this as an algebraic group, one needs to embed. Let's embed GLN into Cn squared plus 1 as, so we have coordinates. Let me write it. This is, how should I write it? Okay. With coordinates and now x11, x and n, right? But also with one more coordinate t. And I will embed it there as follows. So GLN is the set of all elements from this space of dimension n squared plus 1 such that the determinant of A times this parameter t is equal to 1. Right? From this equation, we already see that neither the determinant of A nor t can be equal to 0, and which gives us precisely the description of GLN. And so, and this is already a rational variety, right? A Q variety. Well, and thus it is also a real variety and a complex algebraic variety, right? And definitely is an algebraic group, since those maps, the product and the inversion, is, again, this is just precisely the same. We just multiply matrices and we get polynomial morphisms, again, with coefficients in the field Q, right? So the trickiest part was to get this as an algebraic variety. So this is already a rational variety, and thus an algebraic group. I will write down the following. I will write a general example SOPQ. So SOPQ, this is a group of matrices of order P plus Q, right? Such that A transpose I PQ A is equal to I PQ, and the determinant is equal to 1. In fact, I can consider just any YSOPQ. Let's just consider any OPQ. So I will remove this condition where IPQ can be written in many different ways. I will just write the diagonal matrix. So where IPQ is the diagonal matrix So here I have P elements being equal to +1, and here I have Q elements on the diagonal being equal to -1. So let me highlight that it is -1. Okay. So this is a diagonal matrix. So I consider all matrices that preserve this quadratic form. And so interestingly, I can also include P in one of this being equal to 0. And in this case, if one of this is equal to 0, I will obtain just a standard orthogonal group preserving the standard Euclidean quadratic form, right? Positive definite form defined by the identity matrix. So again, from this description, one basically can see that this is indeed an algebraic group as well. It is defined by some number of polynomials already. It's not one, by some number of equations. It's not a one equation, but find the many. You can compute their number, and you can actually compute the dimension of this Lie group. But what is important that this is an algebraic group. And what is interesting is that when we considered hyperbolic spaces and their isometry groups, we usually in the vector model, right? Or we usually took the subgroup of index 2 that preserves a hyperpoloid. So let me recall why these are interesting in our course. So recall that the isometry group of HD, right, was identified as O prime D1, which is the subgroup of O D1. Okay, sorry, D1 should be here, where O prime D1 is the set of all matrices from OD1 such that A of HD is HD, right? So it leaves HD invariant. But this is no more an algebraically defined subgroup. So we remark that OD1, okay, I omit here actually that this is a group with real coefficients, since as a group with complex coefficients, it's not really interesting. Over C, there is no difference between minus and +1 on the diagonal for this quadratic form, and we will essentially get just the standard complex group ON of C, right? OP plus Q of C. So I'm writing here, I will add this remark here that OPQ is viewed as OPQ of R, since OPQ of C is just OP plus Q of C, right? So if it is important for us that we consider complex places, I will specify it. Otherwise, I will write this as a real Lie group. Okay, so in fact, this is a subgroup of OD1R, but I'm omitting this R because of this remark here. So here now I remark that OD1 is a real algebraic group, and in fact, rational algebraic group. So is an algebraic group. But O prime D1 is not. However, one can identify O prime D1. In fact, it is via the adjoint representation, via the adjoint representation from G, which acts from G to the group of non-degenerate operators on the Lie algebra of G. Again, we do not need it right now. I'm just giving the hint. It requires some background in Lie groups. So one can identify this with this image of the adjoint representation, which is in fact the projective orthogonal group PO D1. So same as here, one can in fact consider the quotient by the center, or so this is isomorphic to quotient of OD1 by plus minus identity, and which is also the adjoint image of OD1, right? So in fact, one can see that the kernel of the adjoint representation will be precisely plus minus identity, and then we get that identification. Okay, and this is already an algebraic group with POD1, which is an algebraic group. So again, as you see, the Lie groups of isometries of like classical symmetric spaces can be viewed as actually algebraic groups, okay, in this like very classical cases, right? Okay, so why it is interesting? This is interesting because of the following property of lattices in Lie groups. So in fact, this is like a part of algebraic geometry, and for those sets, there is this so-called Zariski topology. And I think that, yeah, I have a few minutes more, so I can say that, let me switch back to this left board. So for algebraic varieties, I think I will keep the above, and I will write it down here. The Zariski topology is defined as follows. Closed sets are, these are precisely the closed sets. So algebraic sets are closed. Algebraic sets are said to be closed. So their complements are open sets. This is enough to define topology. And so this topology is quite different from what we have in, yes, by the way, I wanted to say that, and we say that something is Zariski dense if its closure gives us everything, right? So let if X is a closed set, then the subset Y of X is said to be Zariski close or Zariski dense. Sorry, Zariski dense in X if the Zariski closure, I will write it down here. Zariski closure of Y. What is it? Basically, it's the minimal closed set containing, right? The minimal closed set containing Y. Minimal closed set containing Y is X, right? Then we say that
Just make a comment here.
Yeah.
So the Zariski topology is, if algebraic sets are going to be closed in the sort of normal Hausdorff topology, the Zariski topology instead is the smallest topology in which the algebraic sets are closed.
yeah,
Right, so you have as few closed sets as possible. In fact, exactly the algebraic sets are closed.
yeah, I should say that yeah, the algebraic, so it's defined by the fact that algebraic sets are closed, right?
Yes, yeah.
Yeah. So it's not like,
So, but it's sort of, it's important that it's sort of the minimal topology satisfying that fact.
yes, okay, yeah, thanks. So we need to specify that this is indeed a minimal topology defined by this property, but which means that algebraic sets and only algebraic sets are closed, right?
Particularly the Zariski topology is not Hausdorff unless you're working on something finite.
So and only in algebraic sets and only they are closed. Yeah. And yes, and let's try to see the Zariski topology is different. So it's like an important fact. The Zariski topology is really different from the standard real topology. I think I like an example of Z sitting in R. Z in R is a very discrete set in real topology, but it is Zariski dense, right?
C, it's my opinion. It's still Zariski dense there.
Okay. Okay, but yeah, that's true.
It's infinite. I mean,
Yeah, that's infinite. Yeah, we cannot have infinitely many roots of polynomials. Yeah, okay. Well, I can give two examples. Z in R is discrete, but Z is Zariski dense. In R. And same true here. Let us discuss this example. It's a bit simpler. So obviously this is a discrete set, right? We have just points in the real line. Well, basically the explanation for this is the same, but if we have a polynomial that is equal to 0 in all points of z, right, then definitely this is a trivial polynomial. This is a zero polynomial, since every polynomial with real coefficients, it cannot have infinitely many roots. So being Zariski dense, in fact, means the following. So I will highlight it here. So being Zariski dense, in fact, can be explained here, right? So Zariski dense, it means also here. If the polynomial, so Zariski dense. Zariski density implies that if a polynomial p equals 0 on y, right? If p of y is equal to 0, then p of x also is 0, right? The point is that only we should take care of the field, so yeah, it's important that we consider like in which field we have the coefficients of our polynomials. So yeah, but so sometimes people, so for some more advanced proofs or something, people consider K-Zariski closure and something. For our purposes, it's mostly about I think real closure. So yeah, and in fact, I'm interested in this Zariski density because of the following fact. Let me give a statement of the Borel density theorem and then we will make a break. It is the famous Borel's density theorem. So let G be now viewed as a simple real algebraic group. And the gamma be a lattice in G or G of R. And gamma be a lattice. So I remind that this means that it acts as a finite covolume discrete group by isometries on the homogeneous space G mod K, or it is a lattice with respect to the Haar measure on G of R. So in the G of R, we have the Haar measure, and the quotient G mod gamma has finite Haar measure. So then Borel's density theorem implies that then gamma is Zariski dense in the connected component of G. In the connected component of G. This is a very nice fact. So in particular, Zariski density can be viewed as something like gamma does not live invariant any proper plane in the symmetric space X. So this in particular is a consequence of being Zariski dense. So lattices have really nice algebraic properties from this point of view. And so now we will make a break, but after the break, we will discuss how to check the risky density. And it turns out that limit sets, so there is some interpretation of the risky density in terms of limit sets on the boundary. Okay, now let's make a break. All right, so we continue discussing the risky dense subgroups in the isometry groups of our symmetric spaces. We will again focus on the hyperbolic case. So now the main question is, given gamma in isom HD discrete, the risky dense, how can we detect? Okay, well, I would say what can we say about this, right? What can we say about, I don't know, geometric properties of gamma? It turns out that we should use a classification of algebraic subgroups of isom HD. So I will start with the general. I think I will just say that it's a theorem. So let gamma be discrete in isom HD. And let's identify. So let G be just POD1, which is the isometry group of HD. So we start with a general case. Gamma just is a discrete group. Set H, there is a risky closure of gamma, right? This is not a subgroup of G. Then the connected component of H so then the connected component of H is either the product, so it's either a product H sub Y times K sub Y for some, so it's a group of orientation preserving. Let me write it this way. So it's a product where HY is the group of, so it's yeah, this group should be it should be the group of loxodromic, okay, of hyperbolic isometries, the group of hyperbolic isometries whose geodesic axis belong to some plane Y, group of, and here I will write of orientation preserving, right? So these are orientation preserving. Belong to some plane Y in HD, and KY is the compact group, of isometries, of obviously the elliptic isometries, right? Of elliptic isometries, fixing Y. Or it is a group, so it is just some stabilizer, subgroup of the stabilizer, so it should be subgroup HP of the stabilizer of some infinite point, right, of some ideal point, of some point P belonging to the boundary. So the connected component has, we have kind of an algebraic classification of connected algebraic subgroups of G, right? So the Zariski closure is going to be, yeah, and in fact Y is not necessarily to be a proper plane, so the dimension of Y here is between 0 and D, and the inequalities are not strict. I should write it somewhere here. Well, since I didn't specify that, but nevertheless, so 0 less than or equal to dimension of Y and less than or equal than D. So when Y becomes just the entire space HD, this means that gamma is Zariski dense. Otherwise, it is not. Okay, this classification in particular implies that gamma is not Zariski dense, only if it leaves invariant some proper plane for the point at infinity, right? And this theorem gives us the following interpretation in terms of limit sets. By the way, I think I should write here is a group of, right? Since in fact it can be something like I think that there can be many. Okay, I will think about that. So let me give them the following interpretation. So let gamma be discrete in ISOM HD. Then gamma is the risky dense. Is the risky dense in, okay, it is a risky dense in the connected component of G, if and only if the limit set lambda gamma does not belong to any hypersphere of the boundary. So my ideal boundary is the d-1 dimensional sphere. By hypersphere, I mean basically spheres of dimension d-2, right? Of codimension 1 spheres. So this theorem states that, in fact, the limit set should be like distributed over the boundary somehow such that it's not contained in some proper plane. Why? Since if it sits there, then we apply this classification, right? Then it means that if the lambda gamma sits there, then we definitely obtain some proper plane or hyperplane such that my closure, the Zariski closure, is an algebraic group of this type. And then it's not the entire connected component of G, right? So, and well, the converse is also true. If I have something like that, right, I just take the point X from this plane, and then the orbit, the closure of the orbit from the point here definitely gives me the limit set sitting in the closure of Y in the boundary. And this belongs to some hypersphere or a proper sphere in the ideal boundary. So this is a neat equivalent. You might remember that we discussed in particular reflection groups, and for reflection groups, so here proof is apply the previous theorem. And I can write now the following theorem. Let gamma be a reflection group, with fundamental Coxeter polyhedron P. Fundamental Coxeter polyhedron P. Then gamma is a risky dense if P is not, and this is important, so P is neither of this. So P is not a convex cone okay, so yeah, it should not be a convex, just a convex cone with a finite vertex. it is not a cone with an ideal vertex. In this case, this means that gamma is not elliptic Coxeter group. This means that gamma is not a parabolic Coxeter group or a fine Coxeter group. And the third, that it is not a degenerate, is not a degenerate polyhedron. Sometimes it's said to be that P is non-degenerate, right? P is non-degenerate if, so I will add this. So P is non-degenerate if there is no no hyperplane. There is no hyperplane orthogonal to all the walls of P. Yeah. So you see, for reflection groups, the geometric reinterpretation is quite nice. Since for reflection groups, you can construct fundamental domains, there are many tools for that. In particular, there is for groups that are like number theoretically defined, there is a very efficient in practice. Okay, there is very useful in practice Weinberg's algorithm for constructing its fundamental domain consecutively. So you can just check. It's really something that you can code in Sage or, I don't know, Python or Wolfram and check that it's, so it shouldn't be a convex cone. It shouldn't be a convex cone at infinity, since you do not want it to be. Basically, this part, the second part is just coming from here, right? The first part also comes from here. And the third also is from the first part of this theorem, since if it is a degenerate polyhedron, which means that there is a hyperplane orthogonal to all the walls, what does it mean? It means that reflections in the walls of P, they leave this hyperplane invariant, right? Then it's definitely not a Zariski dense reflection group. All right, so this is a description of Zariski dense groups. Generally, Zariski density is actually, it's also quite a strong property. So you can see that many discrete groups that are infinite covolume, they are Zariski dense. So for instance, we discussed the group whose limit set was a counter set, right? It doesn't belong, this counter set doesn't belong to any proper subsphere of the ideal boundary. So it's definitely a Zariski dense group, even despite of being infinite covolume, right? Okay. In fact, I also want to just leave one remark why this rational algebraic groups are interesting. And then we will start discussing. So it's like, again, short intro to arithmetic groups or arithmetic lattices. So let G be a simple algebraic group over Q, algebraic Q group. This is actually a theorem. then G of Z is a lattice in the Lie group G of R. And this is the so-called Borel and Harish-Chandra theorem. Borel and Harish-Chandra theorem from 1962. So if you start with the algebraic groups, then the group of integer points are lattices with respect to the Haar measure and the Lie group G of R. And yeah, and all our famous examples are, okay, many of our famous examples are like that, right? So you can take PSL to Z. It's a lattice in non-uniform lattice, right? In PSL to R, non-uniform lattice. These all are non-uniform lattices. And the second example is just any SLN Z in SLN R. And I can keep going. I can just take any SO T1Z. Great. I can just take the standard diagonal quadratic form with coefficients -1 and +1, the remaining ones, and the group of integer transformations preserving this quadratic form is still going to be a very nice lattice. It will be also a non-uniform lattice. So all these are non-uniform lattices. And this is going to be a hyperbolic non-uniform lattice. It will act, okay, up to finite index, it will act on HD by isometries, and it will have a finite volume fundamental convex polyhedron. So we will discuss arithmetic lattices. So the yeah, I will write down that. Then these such lattices are called, and commensurable with them are called arithmetic lattices. So the definition of arithmetic lattices essentially requires some algebraic group such that our discrete gamma is commensurable with integer points. And hyperbolic space is interesting since, because of this remark, there are, okay, infinitely many commensurability classes of non-arithmetic lattices. So there are infinitely many commensurability classes of non-arithmetic lattices in each HD D greater or equal than 2. So we will discuss this non-arithmetic and, okay, arithmetic versus non-arithmetic probably in the end of this course, probably during the last week. But now I want to say a few words about rigidity and deformation. So rigidity in higher dimensions and deformations in low dimensions. So let me now switch to the left. So now I'm writing about deformations in H2 and rigidity in HD greater or equal than 3. Okay, so what is going on in so basically rigidity, I would say rigidity question is this. Suppose we have two locally symmetric spaces. Locally symmetric spaces, M1 being just X 1 gamma 1 and M2 being X mod gamma 2. So I simplified a little bit. I have this spaces to be common. And I also assume that these are, okay, finite volume, right? So suppose we have two locally symmetric spaces. Okay, non-flat, finite volume, right? Non-flat, negatively curved. And finite volume. So the question is this: when by one of M, sorry, by one of M1, okay, there is some subtlety. I assume that these are torsion-free lattices, but in fact, it's not, doesn't matter, right? I mean, otherwise I should write the orbifold fundamental group by one. Yeah, but I can do it. So, so the orbifold fundamental group of M1 is isomorphic. So when this isomorphism, okay, let me write this, since one is simply gamma 1, right? When this isomorphism implies that M1 is isometric to M2. And here I should write it isometric. So this is the question: when this implication is true? Well, obviously, if these are isometric, then the converse is true, right? So generally, this is not true, and in fact, in this setting, it is not true only in dimension 2. But so let me. Okay, now I will use this board. Now we consider H2, right? In H2. So what's going on in H2? Let us discuss this. In H2, for simplicity, for now, we can probably think about surfaces. And in H2, we have, say, closed, right, surfaces in H2. I can do the following. I can start with the right-angled hexagon, having parameters. So for every A, B, C greater or equal than 0, I have a unique optoisometry, right? We have a unique right-angled hexagon. I should write right-angled right angle hexagon, and I will just draw it here. A, B, C, right? So by gluing, two copies of P, we obtain a pair of pens, hyperbolic pair of pens. A hyperbolic pair of pens with the geodesic boundaries. So with boundary circles. Okay, I can divide it. Sorry, I can divide it by 2 to get the boundary circles. So let me have the hyperbolic length of sides A, B, C, all are taken to be over 2. So with boundary circles, lengths A, B, C. So this looks like that. Okay. And A, B, C. Okay, so to achieve this, I just suggest, what I suggest? I suggest reflecting P here and to glue the sides. So let me draw the picture again. Okay, I will just make it here. So now my sides are, and so which I identify. I glue this one with this one, right? And I also want to glue the orange, identify the orange one here with the orange one here. So this is A over 2, A over 2, and here I get C over 2, C over 2, and B over 2 and B over 2. So after this gluing, I obtain the red arc connecting A and B, right? Yeah, this is my arc. And the orange arc is which one? It's probably from B. Yeah, it's from B to C, right? And actually there is I can take the blue arc or the green in the middle, and the middle geodesic segment here is precisely from A to C. So this means that for every ABC, I'm fixing some parameters. I will get this pair of pens and with prescribed length of the boundary components. So there is this space of deformations, right? I will get topologically the same object, but I will change its geometry. Now what I want to say that every SG can be decomposed into, okay, so by taking this to be strictly positive, I obtain compact guys. So if one of this is 0, there's going to be a cusped pair of pens. So okay, so every closed SG can be decomposed into the union of pairs of pens. I will simply draw this decomposition for S2, okay, for the surface of genus 2. And the decomposition is this. I will divide it here, and then I'm taking, I also cut along this closed curve, and then I should like disconnect these two components on the left side. And well, I can actually do many, but in fact, it's enough to take one more, right? So in this case, the decomposition is simple. So in fact, this means that for the surface of genus 2, I have how many parameters? I have also 3 parameters, right? So this essentially implies that the space of deformations of both this and this surface has dimension 3, right? I have 3 coordinates basically in this space. Okay, topologically, these are going to be the same surface, the same surfaces for any choice of parameters, but their fundamental groups are also isomorphic. However, the geometry is going to be very different since we just simply change the length of simple closed curve here. Okay, now let me add also some remarks about this.
That's the right complex dimension. The real dimension is 16.6, right? That's 2. 6.
Yeah, this is going to be indeed. This is going to be complex dimension apparently, but yeah, but why? These geodesics are traces, basically are traces of elements, right?
Is it maybe? Do you need to keep track of the like all 6 of the sides? This works.
No, I'm not sure. Hmm. I don't know. I think I have an idea. We can probably also do twists around them, no? Yeah, I was a little, indeed. I was a bit wrong about saying about the dimension. Yeah, it should be 6g minus 6. I also remember this formula, but I somehow forgot it here. So I'm okay, I might be wrong, but probably one can also do twists. So yeah, there is a gluing parameter, right? By having this two, so even when we fix the length, right? It's still, I have basically any real number to rotate to glue them together. Yeah. So it gives indeed, and this, yeah, and this holds for any, basically for any cutting orange, red, and green here, and it gives the space of deformation is actually, yeah, generally the space of deformation is of dimension 6g minus 6, right? Fortunately, I don't, yeah, I cannot find the like the short argument right away, but apparently it's like that, yeah. So let me indeed remark that. So space of deformations is, okay, it's like homeomorphic to R6G minus 6, right? Yeah. Okay, but at least we see that it's really large. So in fact, what I want to say that for any choice, so for different, right, for different A, B, C positive, we obtain uncountably many, right? Uncountably many I can probably write gamma ABC, but as we just discussed, they depend not only on ABC, but at least let me include the parameters, right? We obtain uncountably many SG. Okay, S2, right? The surface is S2 with parameters ABC, such that all pi 1 of S2 ABC are isomorphic to the same group gamma 2, but as to say ABC and S to A prime, B prime, C prime are not isometric. Okay, if ABC is not equal to A prime, B prime, C prime after permutation, right?
Like you get the whole map class. This is taking it that you're looking at. So you have a larger thing. A, B, and C are sufficiently short, and the shortest one are different than that works.
Okay, yeah, indeed.
Yeah.
So for
I
different,
would usually think that for this.
yeah, I can just say indeed. So if A is not equal to A prime, and we have ordered triples. Okay, I should write.
And both of them, both A and A prime should probably be very short. Like there's some universal constant sort of thing.
Yeah,
Like
probably.
you want to force them to be necessarily, for example. That will
okay. Yeah.
So.
But yeah, but should I specify it? I don't know. I can say that we're So A and the A prime represent systols. Yeah.
Yeah.
And A prime are systols, which is the lengths of the minimal simple closed curve, right? Okay, minimal lengths of simple closed curves. Okay, so oh. Apparently it's just
Yeah,
that
we're
screen.
just on that machine.
Yeah, it's apparently on that machine. Yeah. Do you hear us and see? Mohammed?
Yes, I'm hearing you.
You see and hear, right?
Yes, I'm seeing.
Okay. Okay. Yeah, that's a bit weird, but we'll just cut that off. Yeah. Okay. Yeah, let me continue. I just need 2 minutes to conclude. Okay, so here we obtain infinitely many closed surfaces with the same fundamental group, but which are isometrically very different. But in H3 and higher, so in H greater or equal than 3, most of rigidity theorem says, okay, states that if pi1 of M1 is isomorphic to pi1 of M2, then M1 is isometric to M2. And I think that apparently I should stop here. Okay, thank you for your attention.